Welcome to the third part of the lecture on designing organic syntheses. In the preceding lesson, we have analyzed this target structure with the help of having in mind using an oxycope rearrangement within our plan for synthesizing this molecule. We noticed that we have the retron of an oxycope rearrangement within this molecule, and this is a carbonyl here, and alpha, beta, gamma, delta, epsilon unsaturation. So the result of our considerations was that we have to synthesize this type of functionalized bicyclic ring system. So, and well, then we should check, and we didn't do that in the preceding lesson, should check what would be the result of the oxycope rearrangement. So reaction conditions: potassium hydride to synthesize the potassium alcoholate, and then heating it up so that the rearrangement can occur. So what would happen? Well, carbonyl group is formed at this position finally. This position is connected with that, So, well, should be right, okay. So, and let's translate that, well, into drawing where we don't have a three-dimensional perspective in mind. So this structure with an oxycope rearrangement would lead to this product, and if we compare that to our initial target, we notice, of course, these are mirror images, right? So that means, well, if we have a racemate as the target, we wouldn't have to care about the absolute stereochemistry. But if we have that as a natural product in mind and want to target it enantioselectively, then this here is the wrong enantiomer to perform that rearrangement. So we need the mirror image. So, and well, in order to get to this substrate, we should consider using, for instance, chiral Lewis acids for enantioselective Diels-Alder reaction. That would be the solution to the problem. Well, next, let us draw again that structure we had a glimpse upon at the first lesson. And now it's time for retrosynthetic analysis to this target molecule. The problem is, where should we start? It's often a very good idea to look at the most reactive functional groups, because the most reactive functional groups you want to introduce into your molecule at the end of the reaction sequence. So, if you want to introduce them at the end of your sequence, well, then it would be, of course, the other way around with one of the first steps in your retrosynthetic analysis. So, and well, for instance, cleaning up or with oxygen and with water, nothing will happen here. It's not possible to hydrolyze here such an ether moiety under moderate reaction conditions. Well, in this case also this is rather stable. You wouldn't mind about that. On the other hand, well, of course, these functional groups here are the most reactive in the molecule. So we should identify what we have here. Certainly a cyclic carboxylic amide. So here we have the amide. On the other hand, an enamine here at that position. So how is an enamine formed? Simply by a condensation reaction. So why not focus on that enamine and the condensation reaction? For that condensation reaction you need a ketone, of course. So let's directly introduce the ketone functionality without thinking about the synthon. It's directly a substrate which would give then, on the other hand, by condensation reaction, the enamine. Okay. So, next step. Where do we have a strategic bond for cleaving within the retrosynthetic analysis and getting to much more simple structure? On the other hand, a bond which is easy to be formed. Well, it could be this one. Donator reactivity here, acceptor reactivity there, and that acceptor reactivity is translated into alpha-beta unsaturated carbonyl compound for the synthetic equivalent. Well, actually, this sequence, this acrylic amide, the treatment of a base and deprotonating here, the overall sequence to this target should remind you of the Robinson annihilation. Yeah? Well, keep in mind that similarity here the acrylic amide, and in the Robinson annihilation you are normally dealing with methyl vinyl ketone. Abbreviated like that. Okay. So, nice initial idea. Now we have to check, would that really work? So, there might be some problems. First of all, if we deprotonate here, we form an enolate. So, and the enolate is a base, and on the other hand, we have this quite acidic amide. So, in equilibrium, we would also get a deprotonation here. That might cause some problems. Might cause occurrence of some competing reactions. Well, we could try that. If it doesn't work, we should improve. So, it might not be necessary directly having the amino group here. We could think about using acrylonitrile instead. Okay? So later on, semi-hydrolyzation of the nitrile group will lead to the amide functionality. On the other hand, well, why not using an acrylic acid ester then we would have this as an intermediary product and could treat that simply with ammonia. Should work. We have to find out the right reaction conditions. Okay. With these considerations, do we already have solved all the problems connected with that step? I'm afraid no. Because if we treat this with a base, how do we get the selectivity that it is deprotonated here and not there? That's a problem. Actually, I don't see any chance for any base to get this preferentially deprotonated here or there. Yeah? So maybe we have to play a trick on that and perform well, it's two-step or multi-step sequence as a one-pot procedure. So, for instance, simplifying it in a retrosynthetic analysis to this alpha beta unsaturated ketone plus this nucleophile, donator reactivity here, acceptor reactivity there, putting on a metal there, and of course M presumably should be some kind of copper complex. An organocuprate we should use for that alpha beta, for this conjugate addition reaction to the alpha beta unsaturated ketone. And of course, if we perform that in a one pot reaction, having then already the enolate in there, well, you have to use some solvents that stabilize your enolate, and then you can trap the enolate directly, well, for instance, with the acrylic acid ester. Well, okay, so we are now down to a structure as simple as this one, a methyl cyclohexanone. Well, let us assume that we try a racemic synthesis, don't care about the absolute stereochemistry here. So, what about this idea, introducing that methyl group also through a conjugate addition reaction? With a methyl cuprate. Wouldn't that be simple? No one with any doubts? So the problem that you have is, where do you get this one from? At least you can't buy it, and there is a simple reason. Under acidic as well as slightly basic reaction conditions, which would of course readily isomerize under formation of the aromatic ring system. Well, it isomerizes simply to phenol. So therefore this is not a good idea, of course. So how should one analyze the synthesis of that molecule? Well, this is so simple. You can be sure that someone has synthesized it and has published it, and so in that case I would just have a look in SciFinder and figure out how they did it, yeah? And maybe also thinking about improving if the reaction sequence which has been done is not satisfying, is not completely satisfying. Well, so simply let us have a look how this is synthesized, already synthesized by others. Well, there is acetic acid ester as one component. This acrylic acid ester derivative as the second component. This is classical carbonyl chemistry. So under the basic reaction conditions with sodium ethanolate in in ethanol. Well, what would happen? This is, of course, the most acidic position, double activated by carbonyl groups. Here you have the nucleophile, and in a Michael addition reaction you get that conjugate addition product. In equilibrium also, every now and then, that CH3 group will be then deprotonated and making another condensation reaction here. So, this will result in that cyclohexane dione like that. So, and after hydrolysis of that ester, so ethanol is formed and a decarboxylation will occur. Remember from organic chemistry 2 that beta keto carboxylic acids are not stable. So we need now some kind of reduction. We need to double bond there and get rid of one of the carbonyl groups. Well, with an ortho ester like that, this is an ortho ester, is an acetal of formic acid ester. Under acidic conditions, you will get this transformation done. Next step is reduce the remaining carbonyl group to give an alcohol. And then simple hydrolysis under slightly acidic reaction conditions will give you that OH group as a leaving group, and the hydrolysis will form our target intermediate. Let us go on with additional strategies and tactics in retrosynthetic analysis. One very simple but often used and very useful is functional group interconversion. Well, often abbreviated as FGI. For instance, in the retrosynthesis books of Stuart Warren. One simple example. Okay, normally you wouldn't bother about the synthesis of this molecule since you can buy that. Yeah, and it's not that expensive. However, imagine we have a more complex molecule in mind with some additional substituents, maybe a long chain, a long side chain or something like that. Yeah, but let's concentrate on these functional groups. So, for instance, we start looking at that disconnection. What do we need here? Donator reactivity for that amino group which we want to introduce. And on the other hand, here, acceptor reactivity. Okay. Looks good on the first glimpse, because donator reactivity is just the natural reactivity for an amine like that. Acceptor reactivity, okay, something like nucleophilic aromatic substitution. However, we have a problem in translating it into synthetic equivalence, simply because, well, let's put on a chloride there as the leaving group, using, for instance, simply ammonia solution. We don't want to use sodium amide. Yeah, this is much too reactive there. Yeah. However, this would react, of course, with the acid. Yeah. So, we would have to protect the acid. Let's try it as an ester. Well, maybe then the nucleophile would still react preferentially than at the ester functionality. So we have a problem there. Let's try the other one. Aniline with a donator reactivity in para position, and this synthon as a fragment, acceptor reactivity here. Well, again, both are the natural reactivities of these positions. However, if you try some Friedel-Crafts type stuff, you have always kinetically preferred the reaction at the free electron pair of that amino group. You are always facing some serious problems. Therefore, functional group interconversion is a good idea, and in this case it's simple changing the oxidation state of a functional group. For instance, here in this case, let's leave the amino group and we go to the oxidation state of a nitro group. Since it's usually no problem for reduction of a nitro group, with hydrogen and an appropriate catalyst. Next step in our retrosynthetic plan, again changing the oxidation state now from the acid functionality. Just go back to the simple methyl group. And para-nitrotoluene is easy to make, of course. No problem in performing this reaction sequence. So, another good idea is looking out for suitable starting materials. So, identifying suitable starting materials. For instance, from the chiral pool. You all know the chiral pool is, consists of all those natural products we can get hands on and having some chiral centers. Okay? We could make use of them, starting that reaction, starting the reaction sequence to our target molecule from a chiral pool compound. Actually, this is then not the pure retrosynthesis anymore. We have our target molecule and we identify a natural product, something from the chiral pool we can buy or we can isolate from nature, and somehow they are related structurally to each other, and we have to connect them within our synthetic plan. We make retrosynthetic analysis and try to get a structure where we know that we get to that structure from the other side, starting from a natural product. Therefore, it's in that case a bidirectional analysis. One example you will find in literature is the synthesis of picrotoxinin. Well, picrotoxinin has been synthesized from the Corey group and also from Barry Martin Tro's group at Stanford. Kurt Hafner was the one who finished that synthesis. Let's draw that target molecule. You will notice this is rather complicated in structure. So, again, Barry Trost and Kurt Hafner. So, they had to look for a natural product from the chiral pool, which has a structural relationship to that, and found that there are some similarities with carbon. And it should be minus carbon. So we have that six-membered central ring with an isopropyl group here. Here the six-membered ring, the isopropyl group, the same stereochemistry, a methyl group at this position, and an oxygen functionalization there. Here the same, methyl group and oxygen functionalization. So bidirectional analysis, in that case having in mind some palladium catalyzed annihilation reactions developed in the Trost group, and the overall synthesis took about 24 or 25 steps. It's not easy to do, of course. So, in addition, stereochemical considerations. Let's explain that with this model compound. So, in this simple, rather simple model compound, we have three stereogenic centers. So, and they are all in close proximity. Therefore, it's a good idea to look for one stereogenic center which could be the control element of a stereochemistry through your reaction sequence. A bond which is easy to make is this one. So a malonic acid ester nucleophile could be introduced here. Easily to be deprotonated, so this is the nucleophile then. We need an electrophilic center here. SN2 process. That means we need the opposite configuration for that leaving group X here. And this lactone is now the target we have in mind if we analyze the next retrosynthetic step. So everyone who knows that reaction, which is called the iodolactonization, now has an advantage, because you then can simply write down simpler structure, this one. So now we know this stereogenic center should be the control element of that sequence. It determines the absolute or the relative configuration here, and if we start from an enantiomer, then we control the absolute stereochemistry of our target molecule. Just for remind you of the Baldwin rules. How do we classify this cyclization reaction? So what kind of cyclization is that according to the Baldwin rules? Well, a 5-membered ring is formed, so we write down a 5. This bond is formed, the double bond is broken to a single bond. That double bond is located outside the newly formed ring, so we have to add an exo here, and the reaction takes place at an sp2 hybridized center. That means a trigonal center. So it's a 5-exo trig cyclization. So the next good idea in retrosynthetic analysis sounds a bit complicated. Identifying strategic bonds by topological criteria. Sounds great, very well educated sounds. Well, actually it's rather easy. We talked already about that. Yeah? A strategic bond is a bond, if you disconnect it, you get really a simplification. If it's not a simplification, then it's not a strategic bond. Okay, that's it. Becomes more clear with this example. So, this one is not a strategic bond. It doesn't become more simple. Well, we could disconnect here, but then we still have that 3-membered ring. But maybe it's possible to simultaneously form these two bonds, and then it makes sense in our retrosynthetic analysis to break those simultaneously. And this looks already much simpler than that. So the idea is, could we use some kind of 2+1 cycloaddition reaction with a carbene or a carbene complex? What I found funny, if we analyze that again, and disconnect So R1 here, this as R2, well, we will notice that both structures are the same. So imagine we would generate this carbene. Would this carbene indeed give that cycloaddition reaction? No, it doesn't, because there is a competing reaction which is much faster. The insertion of the carbene functionality into the neighboring CH bond. This is indeed a very fast reaction. So, you know, in your undergraduate lab, you worked, for instance, you made that cyclopropionation reaction with a dichlorocarbene. This will work. But you can't do that with a dimethylcarbene because of this CH insertion. So therefore we have to modify our plan. We should not have hydrogen atoms here. Well, okay, let's change the oxidation state. This would give then is that correct? Yeah, okay. This would give that cyclopropionation and some kind of reduction which should be chosen carefully, of course, because of that sensitive cyclopropane unit here, should give then that result. And where do you get that kind of carbene from? From that type of diazo compound, for instance, making use of a rhodium or a copper catalyst. Well, of course, one should then further analyze. Yeah? This is still not a simple starting material. So, thank you for listening for today, and see you tomorrow.